Hey guys, and welcome to this video. In this video, we're going to be going through the laws of exponents. Now, to make sure you understand how to work with exponents, I've divided this video into 6 parts. Part 1 will be on multiplying by the same basis. Part 2 will be on dividing by the same basis. Part 3 is on the power law, but specifically multiplying. Part 4 is also on the power law, but specifically dividing. Part 5 is on 0 as an exponent, and part 6 is on negative exponents. This lesson was originally supposed to be 6 separate videos, but while editing, I just decided to make it one video. So during the video, you may hear me make references to other parts of this video as separate videos, but you can just ignore that. Okay, with that being said, let's get into the video. Now, before even getting started on the examples of laws of exponents, let me just explain something quickly about an expression. So, in an expression, this is just one term that we have here. In this expression, you need to understand what the difference between the exponent, the base, and the coefficient is. So let's start off with the base. The base is whatever number or variable is carrying the exponent. And in this case, that would be the x, because the x is carrying the exponent of 2. Okay, so this is our base, because it's carrying the exponent, and this is the 2, because it is on top of the base. And then what about this number over here, 3? Now, the 3 is what we call a coefficient. And the coefficient is just the number that is in front of the variable, the number that is really being multiplied to the variable. Okay, let's get started on the examples. So the first law states that if the bases are the same and we are multiplying, we need to add the exponents. So if we had x to the power of a multiplied by x to the power of b, then this is what's going to happen here. Since the bases are exactly the same, and we are also multiplying, we would just add the exponents. So what would happen is that the base would stay exactly the same, the base is still an x, and then we would just add the exponents. So we have an a plus a b. And a and b are not like terms. Just like we cannot add a dog and a cat and get a cat dog, it's the same way we cannot add an a and a b and get a b. Okay, so a plus b just stays a plus b. And this would just be our answer. So here's an example you can try out. Okay, so since we have a multiplied by a, okay, and the bases are exactly the same, so we're going to keep the base exactly the same. And we can see that we are multiplying, so we need to add the exponents. So 3 plus 4 gives you 7. And that would be your answer. And here's another example. Now, in this example, despite the fact that you have numbers as your bases, because the bases are the same, we still have to use that same concept. It's not a 2 multiplied by 2 gives you 4. It's not that case right now, because as you can see, these bases are the same, but the exponents are completely different. So you have to use that law that states that if the bases are the same and you are multiplying, as you can see, we are multiplying, then you need to add the exponents. So this is going to be equal to 2 to the power of the exponent we have is x and then plus 5. So that is x plus 5. And of course, they are not like terms, so we cannot add them together just like you cannot add a dog and a cat. So this is our answer. And here's another example. So in this example, as you can see, we are multiplying and the bases are the same. And so we know that we have to add the exponents. And I can see an exponent on here, but what is the exponent that is on 3? Well, every number and variable, if it doesn't have a visible exponent, then it means it has a natural exponent of 1. So, because the bases are the same here, we will leave the base exactly the same because we are multiplying, and then we will add the exponent. So that is 1 plus x, which if you like, you could have written as 3 to the power of x plus 1. And the reason why is because this x is positive, so it's a positive x, and this 1 is also positive, so it's a positive 1. So you can also leave your answer like this. Now, with those two last examples, you might just be thinking, what if we had something like 3 times 3? Then what is that? Well, 3 times 3 is 9. But the reason it's 9 is really because of this. If we had to use the laws of exponents to actually find this out, and it's not really because of this, but we can solve this using the laws of exponents. So again, we will see that the bases are exactly the same, so we'll leave the base the same. And then the exponent on the 3, every number and variable has a natural exponent of 1, as long as the exponent is not visible. So there'll be a 1 on here and a 1 on there as well. So that is 1 plus 1, which is 2. And what is 3 to the power of 2? That is 9. Okay, so that would be a way of solving that. So just remember, if you were given a sum like 3 multiplied by 9, then in this case, the bases are not the same. So you would just multiply it normally. And as you can see, the exponents are actually natural exponents of 1. So 3 times 9 is just 27. In this example, we've been given 3x to the power of 3 multiplied by x to the power of 2. Now, in this example, as you can see, the 3x to the power of 3, it has a coefficient of 3. So now that coefficients are being introduced, how you're going to work with them is quite simple. All you're going to do is you will always multiply coefficient with coefficient and variable with variable. So the coefficient of the x cubed is the 3, but what is the coefficient of x squared? Just like when we have a number that doesn't have an exponent, or rather doesn't have a visible exponent, it's the same way if we have a number that doesn't have a visible coefficient, that coefficient is actually 1. So the coefficient in front of x to the power of 2 is actually an invisible 1. So now to multiply this, all we're just going to say is the 3 multiplied by the 1 is just 3. And then we're going to multiply the x to the power of 3 times the x to the power of 2. The bases are the same, so the base stays the same. And we just add the exponents. 3 plus 2 is 5. And that is our answer. In this example, we are given 3 to the power of x plus 4 multiplied by 3 to the power of x minus 2. Do you notice that we are multiplying first of all? And since we are multiplying and we can see that the bases are exactly the same, we're going to keep the base the same and then just add the exponent. So we have the x plus 4, we're just going to say x plus 4, and we're going to add this to x minus 2. We're going to say plus the x minus 2. Now here, I know in some cases you're going to need brackets. With addition, you don't really need brackets. Yes, we are adding this to x minus 2. But the thing is that brackets are not really needed here. If you applied brackets, it wouldn't make a difference. If you distributed this, you would still get a positive x and a negative 2. And that's why when we are adding more than one term to an expression, we do not need to use brackets. We only use this when we are subtracting. So the base still stays exactly the same, and now we just focus on the exponents. We're going to bring the like terms together. We have x and plus x, which is going to give you a positive 2x. And then we have a 4, positive 4, minus 2, which is going to give you a positive 2, and that is our answer. Okay, so before going on to the next examples, I want you to look at these two cases. We're going to compare negative 5 squared to negative 5 all squared. You can first of all take your calculator and put them on the calculator and see what they give for each of these examples. Okay, so now that you've seen what it actually gives you and the fact that it gives you a different answer, here's why it gives you a different answer. Negative 5 squared. Remember that the variable or the number that is carrying the exponent is regarded as your base. So in this first scenario, what would be our base exactly? It would be 5, because 5 is what's carrying that 2, that exponent of 2. So what the calculator understands this as is we have a negative, but then the 5 is being squared. So the negative stays there, the 5 gets squared and becomes a 25. Okay, when things are standing next to each other, they are actually being multiplied. Just like if I had negative a, What this actually means is I have a coefficient of an invisible negative 1 here, right? And the negative 1 is actually being multiplied by the a, and that's why we have negative a. Likewise, with this situation as well, you actually have a negative 1 there that is being multiplied by the 5 squared, which is 25. And so that's why we have that. So negative 1 times 25 is just going to be negative 25. And now if we look at the second scenario, you see that we have negative 5 all squared. What this means is the negative 5 is being squared, not just the 5 anymore. So just like we know that squaring something really means to take that base and multiply it by the amount of times of the exponents that we have, that's exactly what it means here. So negative 5 squared is really saying negative 5 is being multiplied by itself 2 times, so times negative 5. And if you had a negative and a negative number and they multiply, you end up with a positive number, and that's why you end up with positive 25 for this answer. Okay, so I decided to introduce that because we're going to work with some questions that will have these kind of things in them. And I want to include one more thing in this negative 5 squared. The thing about negative 5 squared is there's another way that you can actually rewrite it. Because of the fact that the 5 is only being squared, you could have actually written this, or it could have been presented to you as negative and then bracket 5 all squared. Okay, and this is to indicate that only the 5 is being squared, not the negative 5. The negative is just a coefficient of this expression 5 squared. And here is another example. So in this example, we have that negative again. You're going to have to treat it as if it is a coefficient of this 5 to the power of 2x plus 4. And what do we know about what the coefficients do when we are multiplying? The coefficient here would multiply with whatever coefficient we have here. So the coefficient that we'll have of 5 to the power of 3 is actually an invisible 1. So it's actually an invisible 1 in front of that. So you can see that as the negative 1 multiplied by the invisible positive 1 here. And so we end up with a negative. Then now we can focus on the bases. Okay, so the bases are exactly the same. And so what we're going to do is, since we are multiplying, we are only just going to add the exponents. So we're going to keep the base exactly the same, and we're going to take the exponents. We have 2x plus 4, and we're going to add that to the 3. So this is finally equal to, we have negative, and then 5 to the power of 2x plus 7, and that would be our answer. So you could have written this answer as negative, then in brackets 5 raised to the power of 2x plus 7, because that's the exponent that actually belongs to this base. That negative is a coefficient. It's just in front of the 5 to the power of 2x plus 7. And here is another example. So in this example, we still see a situation of a negative 5. But I want you to look at the coefficient that you have in this first expression over here. We have a 3, okay, which is being multiplied to the other coefficient of negative 5. So when you're multiplying, you need to focus on multiplying your coefficients with your coefficients. In other words, your numbers with your numbers. And then everything that has a variable and exponent, you're going to multiply them together. So what's going to happen here is we're saying 3 multiplied by negative 5 is negative 15. The bases are not the same. Okay, so we are working with normal numbers. And now we're going to look at the variables. So we have variables with like bases. I can see x to the power of 4, which is being multiplied by x to the power of 3. We're going to multiply those together. So when we are multiplying, we are going to add the exponents and keep their base exactly the same. So we have x to the power of 7. Lastly, we're going to deal with the y. Now, take note that we have a y to the power of 5 here, and here we don't have any y. That's not a problem. All this y is going to do is literally just stick to the rest of this expression. Because it didn't multiply by anything, nothing really happens to it, so it stays exactly the same. So we have y to the power of 5. And that would be our answer. And here is another question. So in this question, you see that we have a negative 2 being multiplied by x to the power of 3, y to the power of 6, and then that's being multiplied by y to the power of 2. Always make this simple for yourself by starting with your coefficients. So in other words, if you see numbers that do not have exponents on them, or rather visible exponents, not natural exponents of 1, then you're going to just multiply those. So I see a negative 2. And it's being multiplied by x to the power of 3, y to the power of 6. Now, in this expression that we have here, what is the coefficient that you see here? Okay, we cannot actually see a coefficient because it's an invisible 1 that is there. So I'm really seeing it as I'm going to multiply my numbers all together. And then in the next expression, what do we have here? What is the coefficient that we have, that number in front of your variable? It would be an invisible negative 1, since we have a negative. So what's really happening is negative 2 is being multiplied by a positive invisible 1. You're going to learn to just ignore that soon when there's nothing really there, okay, which is still going to be negative 2. And then you're going to multiply that by the invisible negative 1 that we have here, because every variable and number has a natural coefficient of 1. So that's actually an invisible negative 1 that is there. And so it's negative 2 times 1, which is negative 2, times negative 1, which is positive 2. And now we are done with our coefficients. And now we're going to deal with our variables. So with the variables, we don't have any variable here, and that's okay. But we do have variables here. We have an x to the power of 3. Since we are multiplying all through, we're just going to look for other places that we can also see x. Do you see x anywhere? No. So the x is not multiplying to anything, so it's going to stay exactly the same. X to the power of 3. Nothing happened to it. Then we have the y. And in this y we have, here we don't have a y in that expression. Here we have a y to the power of 6. And in this part we have a y to the power of 2. We're going to just multiply those together. Y to the power of 6 times y to the power of 2 is going to be y to the power of 6 plus 2 is 8. And that is our answer. And here's another question that we have. Okay, so now to solve this, to simplify this, again, we are going to multiply coefficients altogether. In other words, number times number. Okay, we are only multiplying numbers. So first we have the 4, which is being multiplied by negative 3, and that gives you negative 12, which is being multiplied by 2, which gives you negative 24. So those are our numbers done. And then we're going to multiply our variables together. So we have an x. Which other x do we have all through here? We have another x over here. And that's the only place there's an x. So x times x is going to give you x squared. And we're done with the x's. And now we're dealing with the y. We only have one y there, okay, all through. So it just stays the same. It didn't multiply by anything, so it will stay there. And then lastly, we have a z. It also didn't multiply by anything, so we're going to leave it there. We have the z. Okay, so I just wrote like that so that you don't mistake it for 2. So that would just be our solution. Hey guys, and welcome to part 2 of my lesson on laws of exponents. In this video, we're going to be working on the exponential law that states that if the bases are the same and we are dividing, then we are going to subtract the exponents. So here's our illustrative example. We have x to the power of a being divided by x to the power of b. Please note that this could have also been written as x to the power of a divided by x to the power of b. You would notice that the division symbol looks like this. So we have a numerator over a denominator. Okay, so if we have x to the power of a divided by x to the power of b, we can see that the bases of this expression are the same. So we're going to keep the base exactly the same, and we are going to subtract the exponents because we are dividing this time. So that is going to be the top exponent minus the bottom exponent. So the exponent on the numerator is the a, and then that's going to be minus b. And that's what we will get for our answer. So here's an example. We have a to the power of 4 divided by a to the power of 3. So as you can see, the bases are exactly the same. And so, since we are dividing, we're going to keep the base the same, and we're going to subtract the exponents. So that is a 4 minus 3, which gives you 1. But the thing is that when you have an exponent of 1, you don't have to actually write that exponent. You could just leave it like this, because we know that on top of the a, the exponent of the a has a natural exponent of 1. So whenever you have an exponent of 1, you don't have to actually write that down. You can just leave the answer like that. So our answer is just A. Here's another example. So in this example, as you can see, we have a base of 2 being divided by a base of 2. So the base would stay exactly the same, and then we're just going to subtract the exponents. Remember, the order is the top minus the bottom. So that is going to be x minus 5. And that would be our answer. Here's another example. Okay, so in this example, I've introduced a coefficient. Remember, how the coefficients work is whatever operation we are working with, you're going to start with those coefficients first. So we have a negative 3 on top. What is the coefficient on the denominator though? Because we cannot see a coefficient, their number being multiplied by the x to the power of 2, it means there's actually an invisible 1. So here you would just ask yourself, what is negative 3 divided by positive 1? And negative 3 divided by 1 is just negative 3. Then we would work with the variables. So the x to the power of 4 divided by x to the power of 2, that would stay x, and then you would just subtract your exponents. So 4 minus 2 is 2. And this is our answer. And here's another example. So in this example, we have negative 5 to the power of 2x plus 4, and then that is being divided by 5 to the power of 3. Okay, so I know that there's a negative in front of the 5, but remember, what is the base that is actually carrying this exponent? That would be the 5, not the negative 5. So the negative is just a coefficient. It's just an invisible negative 1 that is being multiplied to this 5 to the power of 2x plus 4. So how we would work with this is we need to work with the coefficient separately. We're really just looking at this like this. We're saying the negative 1 divided by that positive invisible 1 there, and that will still give us a negative, okay? It's really negative 1, but we're not going to put the 1 there. Then we have the two things that have the same bases, the 5 to the power of 2x plus 4 being divided by 5 to the power of 3. And so we're going to use the law of exponents here in law 2. So we're going to keep the base the same, and then we're going to subtract the exponents. So that is the top exponent, which is 2x plus 4, minus the bottom exponent, which is minus the 3. So do you see that there's no use for brackets here? Because we're just subtracting it by one single term. And so this would be equal to, and we're going to have a negative 5 raised to the power of 2x. And then what is positive 4 minus 3? That gives you a positive 1. And that would be our answer. Here's another example. Okay, so with this example, we have 2 to the power of x minus 4 being divided by 2 to the power of x minus 6. Again, as you can see, the bases are exactly the same, and we are dividing, so we are going to subtract the exponents. And so this is going to be 2 to the power of x minus 4. That's the top exponent. And we need to subtract this by the bottom exponent. But do you notice that the bottom exponent has two terms? Remember, terms are separated by plus and minus signs, okay? So because I have a minus sign in the middle, it means there are two terms. That positive x is one term and the negative 6 is another term, okay? When you have multiple terms and you're subtracting by multiple terms, you cannot just put x minus 6, because if you do this, then it means that this expression is only going to really subtract by the x, because it's just that and then minus x. You just put the 6, the negative 6 as it was. That's not how it's supposed to work. It's supposed to subtract by this entire expression. So what you're going to do to make sure that it actually does subtract by that entire exponent is you're going to put brackets in front of that exponent. That way, the negative gets to have an effect on both terms in this expression. So what will happen is we will just have the 2 raised to the power of x minus 4, and then this negative is going to be distributed into this expression. So the negative multiplies to the x and becomes a negative x, and the negative multiplies to the negative 6 and becomes a positive 6. And then we are just going to be left with 2 to the power of, and we're going to put the things that are like together. So we have an x and we have a minus x. Always take the sign in front of it. And x minus x is 0 because it's really the same thing subtracting. And then we're going to have to work with the numbers. We have a negative 4 plus 6, okay? You can see that as a positive 6 because it's positive, minus a 4. So positive 6 minus 4 is what? We have 2 to the power of 2. And 2 to the power of 2 is just equal to 4. And that's our final answer. All of that expression was really just equal to 4. Okay, moving on to the next one. Okay guys, so here's another thing that I want to quickly add. Sometimes you can actually simplify these quicker. Now, it just depends on the stage that you're at. If you are in grade 8 or grade 9, you'll probably still be working through this the same way that I'm working through it in the video, meaning you're going to say that exponent, of course, when you leave the base the same, minus this exponent. But there are also other ways of simplifying this quicker, okay? You could have separated these expressions. So I'm just saying this for anybody who's maybe in grade 10 or grade 11 and you already worked through this in a quicker way. So I could have just separated this by saying 3 to the power of x, and that is being multiplied by 3 to the power of negative 3. Because the only way I could have gotten 3 to the power of x minus 3 is by having this. You see, the rule states that if the bases are the same and we are multiplying, then we add the exponents. So if I had to try and get back to this, I see the bases are the same and I'm multiplying, so I leave the base the same and say x plus negative 3. But you see, if you add by negative 3, that's just going to become a negative. So negative 3. That's why we get back to that. So you could have separated them like that. And so if you separate the one on the denominator, it would be 3 to the power of x multiplied by 3 to the power of negative 4. And then you can see that on the numerator and the denominator, those two would cancel because they're exactly the same. And then you would have to just divide that. So you would use the rule that the bases are the same. So 3 to the power of negative 3. And you know it's going to say minus negative 4, which will become a plus 4. And so 3 to the power of negative 3 plus 4 is 3 to the power of positive 1, which you don't have to write. And that would be your answer. And here is another example. But please notice that in this example, we actually have two examples that look very similar. But you need to be careful with the coefficients and how they actually divide. Okay, so in the first example, we have negative 15 divided by the negative 5. If you take negative 15 and you divide it by negative 5, your answer is just going to be a positive 3. Okay, it's going to be a whole number, and 15 is actually divisible by 5. So that would be it for the coefficients. Then we'll go to the variables, and we have x to the power of 4 being divided by x to the power of 3. Again, we're going to keep the base exactly the same and subtract the exponents. If you say 4 minus 3, it gives you 1. But remember, you don't have to write that 1, okay, because it's there, it's an invisible 1. And then we have y squared divided by y. Well, y has an exponent of 2, and the y here has an invisible exponent of 1. So that's really 2 minus 1. So we still have y, and 2 minus 1 is just 1. We also don't have to write that exponent because it is a 1. So that would be our answer. In the second question, however, notice that we have a negative 5 divided by a negative 15. Already thinking about that, you can see now that the numerator is smaller than the denominator. Well, obviously, I mean the actual value of 5 is smaller than 15. So in this situation, when you see immediately that the absolute value of the numerator is actually less than the denominator, what's going to happen is, you know, you're not going to end up with a whole number, you will end up with a fraction. So what you're going to have to concentrate on is, what is common? What is the highest common factor between 5 and the 15? Okay, so they're both negative. So negative divided by negative would be positive. But then the common factor between 5 and 15, the highest common factor, would be a 5. So we're going to take 5 and we'll take 15 and we're going to divide both that numerator and the denominator by 5 because 5 is the highest common factor. So 5 divided by 5 really just gives you 1. And 15 divided by 5 gives you a 3. So this is what we have on the numerator and on the denominator. Okay, and then we would work on our variables. So the variables would work like this. You still have an x to the power of 4 being divided by x to the power of 3, which we know from the previous example that this is going to just be x. Where does this x go? It goes on the numerator. When we divide anything naturally, it goes onto the numerator. So we just have an x there. And the y to the power of 2 divided by y is just going to be y. And that also goes on the numerator. When you divide naturally, it just goes on the numerator. So it really means that you see this answer that we have here, because it divided normally without leaving a fraction, it is actually on the numerator and its denominator is an invisible 1 if you wanted to write it as a fraction. But this is the answer as it is. So with this one, you can actually simplify this further. The reason why is because you have a 1 in front of xy. The only time we actually leave a number in front of a variable is if it is anything other than positive 1. Okay, in this case, what you're going to do is, it's kind of like saying 1 multiplied by x. It's just going to be x. So you just have x, y over 3. And that is going to be your answer for that question. Okay, and here is another example. So in this example, as you can see, the coefficients of the variables in this, we have negative 16 and we have 10. We have to divide negative 16 by 10. But the thing about this expression is that on the numerator, if you compare the numerator, the coefficient, this negative 16 and the 10, if we're looking at the absolute value, of course, so the 16 and the 10, you can see that the numerator actually is bigger than the denominator. But they are not numbers that can properly divide into each other and just give you a whole number. So what do you do in this situation? Well, you're just going to do exactly what we did in the previous example. You're going to look at 16 and you're going to look at 10 and ask yourself, what is the highest common factor between both of them? There's a method where you can use a calculator to do this, and then there's a method where you can actually do this freehand. Okay, so I'm going to do two methods just for any person in a school where you guys aren't really allowed to use a calculator at the specific phase. Let's see how this is going to work. First of all, we know that we have a negative divided by a positive, which is going to give us a negative. So I'm already going to consider that this fraction is going to be negative. And then we have 16 divided by 10. If you wanted to simplify this using the calculator, you just put 16 over 10 on the calculator, and whatever fraction it gives you, you take that. When I put 16 over 10 on the calculator, I get 8 over 5. So I would know I have an 8 on the top and the 5 on the denominator. But how would we know how to find this if you weren't using a calculator? Well, you're going to have to find the highest common factor of 16 and 10. So we're going to look at the factors of 16 separately. So I'm only going to show this once. Okay, so how you find the factors of 16? A quick way of finding factors instead of naming them each is like this. You're going to take 16 and you're going to divide it by a bunch of numbers that can actually go into 16. I will try 16 divided by 1. If I say 16 divided by 1, I will get 16. What this means is that both 1 and 16 are factors of 16. Since if I say 16 divided by 1, it gives me 16, that it means that 16 can also divide by 16. So my factors are 1 and 16. Then to get the next factor, I'll try dividing it by 2, and I'll get 8. So that means my factors are 2 and 8. If I tried dividing by 3, it wouldn't work. But if I tried 4, it would. It would give me 4. So that would be 4, and I can't write 4 twice. And I know that 5 won't work, 6 won't work, 7 won't work, and I already have 8. So these are my factors of 16. Factors of 10 would work exactly the same way. The factors of 10 would be 10 divided by 1, which is 10. So my factors are 1 and 10. Then 10 divided by 2 is 5. So my factors are 2 and 5. And as you can see, 2 and 5 very close to each other. If I tried 3, it wouldn't work. If I tried 4, it also wouldn't work. So if I tried 5, which I already have, it would work, and these would be my factors. Okay, so that is very useful for grade 8s and 9s, I guess, to find factors easily. And then looking at these two groups, you're just going to have to look at what is the highest common factor. The highest common factor between 16 and 10 would be 2. There's no other factor that is higher than that. Okay, that would be common in both. And so since we know that 2 is the highest common factor, we'll just divide negative 16 by 2, which would give us 8, and then divide 10 by 2, which would give us 5. And that's how we'd get that. Okay, so I'm only explaining that once because you see it takes too much time to deal with. And just in case most of you at this point are allowed to use calculators. Okay, so we got our numerator and denominator with regards to our coefficients, and then we're going to deal with the exponents, or rather the variables and the exponents. So x to the power of 3 divided by x, you see that the bases are the same. It will stay x. Remember, it goes to the numerator. Okay, to the power of 3 minus the exponent here, which is a 1. 3 minus 1 is 2. And then we do the same thing to y. So y to the power of 6 divided by y to the power of 2 would be y to the power of 6 minus 2 is 4. And so now you see in this expression, if you say negative 8 times x to the power of 2, it's just going to stay negative 8 x to the power of 2. So we can't really change that. And so in this case, this is all we have. Negative 8 x to the power of 2 y to the power of 4 divided by 5. And that is our answer. And here's another example. Go for it. Okay, so you see in this example, our coefficients 2 to the power of 5 and 2 to the power of 3, they are bases, okay? Bases that are exactly the same. So we're going to have to keep the base the same here. And then we're going to have to subtract the exponents. So 5 minus 3 gives you 2, okay? And then we have here the x to the power of 2 divided by x. Okay, exactly the same thing. The base is exactly the same. We'll just say x to the power of 2 minus the invisible exponent of 1, which is just to the power of 1. You don't have to write that. Then we have a y to the power of 4. Now, did the y to the power of 4 divide by anything? No. So the y to the power of 4 is going to stay exactly where it was. It was initially on the numerator, so leave it on the numerator. It's going to stay y to the power of 4. Remember, everything that is here is naturally on the numerator because they divided perfectly. Then look at this expression. Is there anything that actually can be simplified? It's the 2 squared. The 2 squared actually has a numerical value. We can just say 2 squared is equal to 4. So our answer is 4x and y to the power of 4. Okay guys, so I decided to add this part just in case this may come up in any example exercise that you're working on. If you have this type of situation, as you can see, the bases here in the numbers are not the same. There's nothing you can do. You cannot divide things that do not have the same basis, as in using that rule that the base will stay the same. So what you're going to do here is just simplify whatever you need to simplify. So I have a 2 squared. I could simplify that. 2 squared is 4. And so I have 4 over, and then I have 9. Then I can look in 4 and 9 and see, can they actually simplify? No, they can't because they do not have any common factor. So that's just 4 over 9. And then you have your x's, of course, that is an x squared divided by x, which is going to give you an x. And you have a y on the denominator, which did not really go anywhere. It didn't divide by anything, so it stays there. Likewise, if you had a case like this, as you can see, the bases on the coefficient are not the same. So we will just simplify it. What is 5 squared? That is 25. And you still have x, y to the power of 4 over what is 3 to the power of 3. That is 27. And as you can see, 25 and 27, they cannot divide. So this would just be your answer. Here's another example, and you can go ahead and go for it. Okay, so in this example, we're dividing again, and you can see some bases are the same. So we have x to the power of 4 being divided by x to the power of 2. We're going to say x to the power of 4 minus 2 is 2. Then on the numerator, do you notice you have a y to the power of 3? Is that being divided by anything else? Does it have a like base on the denominator? No, it doesn't. So keep it where you found it if it didn't divide by anything. It will stay on the numerator, it's y to the power of 3. But then now you see that we also have something else here. We have a w to the power of 2. And that is also not dividing by anything. So that needs to stay exactly where it was. It was on the denominator, so leave it on the denominator. It's going to just be on the denominator, so over w to the power of 2. And that is our answer. Here's your next example. Okay, so here we have an 8 divided by a negative 12. So I'm already starting with the numbers. We're going to divide the numbers. As you can see, 8 can't really go into negative 12. However, they do have things in common. So you can use the calculator method or you can use the long method if you're not allowed to use a calculator, as I have shown previously in this video. So if you use any of those methods, you'll find out that 8 divided by negative 12 is just going to give you a negative 2 over 3. So we can't put the negative here. You can give it to one of the numbers. It's still fine. The fraction is still negative. Okay, and then we have, so let's extend that. Then we still have our variables. So we have the a to the power of 3 divided by the a squared, which is just going to give you a to the power of 1. You don't have to write that. And then we have a b to the power of 4, which is not dividing by any b on the denominator. So that stays b to the power of 4 on the numerator because that's where we found it. And then we also have a y to the power of 2 being divided by a y. So y squared divided by y, that is 2 minus 1, which just stays y to the power of 1, and you don't have to write that. Then, do you see that on the denominator you have a c, which didn't divide by anything. So you have to leave it exactly where you found it. It didn't divide by anything, so it stays on the denominator as a c. And that would be our answer. Hey guys, and welcome to part 3 on this series on laws of exponents. In this video, we're going to be working on the third law of exponents, which states that if an exponent is raised to another exponent, then we multiply the exponents. So if we were given x to the power of a, and this is being raised to the power of b, what's going to happen is that you see parentheses or brackets. They really just mean to multiply. But what is multiplying in this case? Well, as you can see, you don't have a base here. You have an exponent. You also have an exponent on the x. So what's actually multiplying would be the exponents. So we have the a multiplied by the b. So our answer is going to stay x. We still have a base of x, but now the a multiplied by b gives you ab. Now here's another scenario that this concept can also be used in. And really, it's not another scenario. It's really the same scenario. But in this situation, we have more than one base inside the brackets. So what would happen is because these two bases, these two variables are being multiplied, that's why they're sitting next to each other and we don't have a plus or minus sign in between them. Because they're being multiplied, the same rule will apply. Each base has an exponent, and that exponent would get multiplied by the exponent outside the bracket. So we would just have the x to the power of a multiplied by c, which would give us ac, and then we would have the y to the power of our b also multiplied by the c, which would give us y to the power of bc. So both of these scenarios are going to be used throughout this video because they're really speaking about the same law. So here is our first example for this video. Okay, so we can see that the 2 is being raised to a 3, and that is being raised to the x. So the 3 would multiply by the x, and so we would be left with 2 to the power of 3 times x, which is 3x. Here's another example. Go for it. Okay, so in this example, you see that we have an exponent on the 2. And this base and exponent is being raised to another exponent, but this exponent has 2 terms. So what will happen here is we still have the 2, and then the 3 needs to multiply to the x, and it also needs to multiply to the positive 1. So 3 multiplied by x gives you 3x, and then the 3 multiplied by positive 1 would give you positive 3, and that would be our answer. Please take note that this expression could have also been expressed like this. In this case, we have the 2 to the power of 3, but that exponent of 3 is being multiplied by x plus 1. So it would still be the same situation where we would have to leave the base, and we're going to have 3 multiplied by x, and that gives you 3x, and 3 multiplied by positive 1, which gives you a positive 3. So we will still distribute this 3 into this binomial. Okay, so before getting on with the next example, I just wanted to show you this scenario, and just so that you can understand this concept. When we have negative and then bracket 3 to the power of 2, where do we start? Do we start with the negative and multiply it into the 3? Or do we start by squaring this 3? Okay, so to make this easier to remember, let me give you a theory about exponents, or rather something that I've just decided to use to remember this law better. You see exponents. See it as exponents are very jealous and possessive. Okay, the exponent, and the reason why is because the exponent is nothing without its base. If I just wrote 2 as an exponent, we wouldn't even know that's an exponent. You would just think that's the number 2. Unless I put a base, and then you realize, oh, this is actually an exponent. So because the exponent needs the base in order to even be an exponent, I say that it's very jealous and possessive. And so no matter what is going on in the expression, the exponent will always be applied to the base first before any other thing can touch it. That's of course if you have nothing to simplify inside your brackets. So if you look at that again, what do we start with? Do we start with the negative or that exponent of 2? We start with the exponent of 2. You're going to first square this. You're going to apply that square into the 3. And this is actually what happens. It doesn't really just get squared. What happens is this. We still have the negative outside the bracket really. And then the exponent on 3 is an invisible 1. And that 1 multiplies with the 2. And then this 3 to the power of 1 multiplied by 2 is going to be 3 to the power of 2 that we will get. And so now you can go ahead and simplify that. 3 to the power of 2 is 9. So we still have the negative in front as the coefficient. And then 3 squared is 9. And that would be our answer. Okay, so with that being said, we can get on with the next example. Okay, so this is the example that we have, and you can go ahead and work on this one. So in this example, we have a base. Of course, we have a coefficient outside, but we have a base, we have an exponent, and that is being raised to another exponent. Remember, the exponent is very possessive. It is nothing without its base. So what's going to happen is the exponents get multiplied first. So we're still going to have the negative, and then we have a base of 5. Which is being raised to the exponent of 2, and 2 gets multiplied by the 2x, the other exponents that we have, and it's also going to get multiplied by the negative 3, or it's going to multiply to the negative 3. And so we're going to have 4x, and then 2 times negative 3 is negative 6, and that would be our answer. Here is your next example. So in this example, we have 2 bases inside this bracket. So what's going to happen is each base, its exponent is going to multiply with whatever exponent is outside the bracket. So the x gets multiplied by the 4, and so we're going to have 2 raised to the power of x multiplied by 4 gives you 4x. And then the 3 as well, that's going to happen. So the 3 has an exponent of y, that y will multiply to the 4. So we'll have the base of 3, and y times 4 is 4y. And that would be our answer. Here is another example. You can go ahead and pause the video and actually attempt to work this out. Okay, so this is what we have. We have 2 bases as well inside this brackets. What's going to happen is whatever your base is, you're going to look at that exponent and it's going to multiply with whatever exponent is outside the brackets. So we still have the 5, and now 1 minus x has to multiply to 3. Well, you have to make sure that the 1 and the negative x gets a chance to multiply to the 3. So what's going to happen is that you're going to have to say the 1 multiplied by the 3, which would give you a 3, and then the negative x multiplied by the 3, which would give you a negative 3x. Then we have this is being multiplied by 3 to the power of, so with the 3, its exponent is x plus 2. So the x is going to get a chance to multiply to the 3, which is going to give you 3x. And then the positive 2 also multiplies to the 3, which gives you a positive 6. And this would be your answer. And I really just have a dot there just to show that they are being multiplied. And that would be our solution. In this example, we have 2 to the power of 4 multiplied by 7 to the power of x, which is all being raised to the power of 3x minus 2. Okay, so we're going to be looking at the bases first. We have a base of 2, which has an exponent of 4. That exponent needs to multiply with whatever exponent is outside the bracket, which is all of this. Okay, so what's going to happen is we leave our base of 2, and then the 4 is going to have to multiply to the 3x and the negative 2. So 4 multiplied by 3x is going to give you 12x, and then 4 multiplied by negative 2 gives you negative 8. And this is being multiplied by, and again we have our 7 now. Our 7 has an exponent of x. So the base stays 7, and then we're going to have x being multiplied by the 3x, which gives you 3x squared. And then the x multiplies to the negative 2, which gives you negative 2x. And that is our answer. Here is another example. Okay, so in this example, we have one base. But this base is being raised to an exponent with 2 terms. And that entire expression is being raised to another exponent with 2 terms. What's going to happen is your exponents still have to multiply. But now you have 2 binomials multiplying. Okay, so what happens is our base still stays the same. But you're multiplying x plus 4 by x minus 3 because they are binomials. And you need to make sure that each term gets a chance to multiply to the other term. You're really just going to have to multiply it like this so that both of them can actually get to multiply to each other. So we're going to distribute them like this. We have 3 raised to the power of, and x is going to have to multiply by x, and that will give you x squared. And then the x here multiplies by the negative 3, which gives you a negative 3x. And then the 4, positive 4 multiplies by the x and gives you a positive 4x. And then the positive 4 multiplies by the negative 3 and gives you a negative 12. And then we see that in this expression, we can actually simplify that exponent. So we still have a base of 3 raised to the power of x squared, and then negative 3x plus 4x is going to give us a positive x, and then we have minus 12. And this is our expression. Okay, so you don't actually have to rewrite this like that. I was just trying to show you what happens to those 2 binomials and how they multiply. You could have actually distributed them from here. You could have multiplied them out like that, and that would have been fine. Okay, so here's the next example that we have. You can go ahead and work on this one. Okay, so in this example, we have a couple of things going on inside the bracket. We have a number right now, okay? So remember that everything inside the bracket, as long as it is a base, it has an exponent. And that exponent is going to multiply with this exponent of 2 on the outside. So let's look at 3 first of all. 3 is a base, but what is the exponent on 3? It is an invisible 1 that is there. So what happens is you have 3 raised to the power of 1, and that 1 multiplies by the 2. So you're still going to have your base of 3, and 1 times 2 is 2. And then with the x, the same thing happens. We have x as a base, so the exponent of 5, let me put that in purple, of 5 is going to multiply to the exponent of 2, and that's going to give us x to the power of 5 multiplied by 2 gives you 10. Then we have the y. The y has an exponent of 2. That exponent is going to multiply with that exponent. So we have y to the power of 2 times 2, which is 4. Then look at this expression. Can you simplify this any further? Yes, we can. We can simplify this by saying 3 squared, that actually has a numerical value, which is 9. So 9, x to the power of 10, y to the power of 4. And that would be our answer. And here is another example. So in this example, we have 2a cubed y squared, and all of this is being raised to the power of x plus 2. So we're going to look for our bases. We have a base of 2. That has an exponent of an invisible 1. And so that invisible 1's exponent is going to multiply with whatever exponent is outside the bracket. So we're just going to have our 2, and that invisible 1 needs to multiply with this expression. So that 1, it has to get a chance to multiply to the x and the 2. So 1 multiplied by x would give you x, and 1 multiplied by 2 would give you positive 2. Then we come to the a to the power of 3. That exponent of 3 is going to have to multiply to the exponent outside. So we still have the a, and then to the power of 3 multiplied by x is 3x, and 3 multiplied by 2 is positive 6. And then this is also going to happen with the 2. So the 2 is going to multiply to the x, which gives you, and we still have our base of y, of course. So 2 times x is 2x, and then 2 times 2 is positive 4. And so this would be our solution in this case. You don't actually have to simplify that as a number. Even if you left it like this, it would be fine. Okay, so now I want to speak about a concept that can sometimes seem very confusing. We have negative, then a raised to the power of 2, okay? And versus a negative a raised to the power of 2. First of all, I want you to look at the exponent in this first question and ask yourself, what base belongs to this exponent of 2? What is being squared? Well, in this case, what is being squared is actually the a, the positive a. The negative is just a coefficient. It's outside the bracket. It's not being squared. So what would happen is you still have your negative outside, and so a gets squared. A has a natural exponent of 1 on it, and so the 1 multiplies by the 2, and so we still have an a as the base, and 1 times 2 is 2. So our answer is negative a squared. But in the second scenario, you see that we have an exponent of 2. So what is being squared? It's the negative a that is being squared. So what happens is when a negative value, whether it is a number or a variable, when a negative value is being raised to an even exponent, okay, it will become positive. So what happens here is this becomes a positive a squared. Now, why does this happen? Well, because if you have negative a all squared, we're really just saying what we are multiplying 2 times by itself is negative a times negative a. That's what we're doing. And so when you have a negative number multiplied by a negative number, it becomes a positive number. And this would give us a positive value. So positive a squared. Also remember that this rule applies when you are raising a negative base to an even exponent. It doesn't just have to be 2. It can be 4, it can be 6. As long as it is an even number, then that base is going to become positive. Now here's another way of doing this. Let's look at that exponent of 2. What exactly has the exponent of 2? What's carrying the exponent of 2? That would be the negative a. So what's actually happening is negative a is being squared. Negative a squared would be equal to a squared. But I want to show you why this happens step by step. You see, if you're looking at the negative and you're looking at the a, what we don't see is that there's actually a coefficient in front of the a. The a can be seen as a variable on its own. And the negative can be seen as a variable on its own as well, a number really on its own. And so that negative actually stands for a negative 1. That's what's in front of the a negative 1. And so what happens is the negative 1, that number gets squared and becomes a positive 1. And the a also gets squared. It has its exponent of 1, which multiplies to the 2 and becomes an a to the power of 2. But you see, we don't have to write 1a squared. We leave the 1 out because even if we wrote a squared, we all know that there's actually a 1 in front of it. And so that's why this is just a squared. That's actually what happens. Okay, so that's actually what happens. So just remember, whenever you have a negative variable or number that is being raised to an even exponent, it's going to end up becoming positive. Okay, so here are two examples that we can compare. You can have a go at this one and then play for the solution. Okay, so in this question, the first one, we have negative a to the power of 3 or raised to the power of 2. If you use that whole system that this negative is actually a coefficient of a to the power of 3, all you could have done here is say that because you know this is a negative and it's actually a negative 1, that gets squared and it becomes a positive 1, which I can choose to write or ignore. But if I write it down as positive 1, then I know that this positive 1 is still being multiplied by the base of a, and a has an exponent of 3, which needs to multiply with its exponent of 2. And so 3 times 2 is 6. So this is a to the power of 6. So 1 multiplied by anything just stays the same. So 1 times a to the power of 6 is just a to the power of 6. And that's why that's positive. And then in the second example, we have this. Same situation. I know there's a number, but it's still the same situation here. So you can just look at this as a coefficient, a negative 1 that is a coefficient of 5 to the power of 3. It's being multiplied by 5 to the power of 3. So that negative 1 gets squared and becomes a positive 1, which I can choose to write or leave out, but I'm just writing it to show you what's going on. You don't have to be writing it. You can just acknowledge that it gets squared and it is positive. Okay, and then we have the 5 raised to the power of 3, and that exponent has to multiply with that outside exponent. So 5 to the power of 3 times 3, we're going to have 5 to the power of 6. 1 times 5 to the power of 6 is just going to give you 5 to the power of 6. And 5 to the power of 6, if you put that onto your calculator, has a numerical value of 15,625. Okay, so 15,625. In this video, we're going to be working on really a follow-up on part 3's law. So part 3's law dealt with the power rule, where we have a base raised to an exponent, and then that entire expression is raised to another exponent. Well, in this law, what we're going to have is a fraction being raised to an exponent. So here's an illustrative example. If we have x over y and all of that, the numerator and the denominator, are being raised to the power of a, what happens? Well, the x is a base, and so it has an exponent. The exponent on x is actually an invisible 1, and the exponent on y is actually also an invisible 1. So both those exponents are going to multiply with the exponent outside the bracket, which is the a. So we're just going to have the x, and we have 1 multiplied by a, which gives us a, over the y, and we also have the 1, which will multiply by the a, which would give us a. And that would be our expression expanded. Here's another example. So using your knowledge on the previous video, you can go ahead and give this one a try. So in this example, everything that is a fraction, okay, all of this, they're all being raised to the power of 2. So what's going to happen is we're going to catch each base. 3 is a base. What is the exponent on 3? There's an invisible exponent of 1. So we're just going to have the 3 being raised to the power of 1, and that 1 multiplies by the 2, and that gives you 2. And then we have the x as a base. It has an exponent of 2, and that multiplies by the 2. So that is x to the power of 4. And then on the denominator, again, we have a base of 2. That is also going to have an exponent, an invisible exponent of 1, and that 1 multiplies to that 2 over there. So we have 2 raised to the power of 1 times 2 is 2. Then again, we have y, and that exponent of 3 multiplies to the 2, which gives us a 6. Then we just look at this and see, is there anything else we can simplify? Yes, we can actually simplify this 3 squared and the 2 squared. So 3 raised to the power of 2 is 9. So we have 9x to the power of 4 over 2 raised to the power of 2 is 4. So y to the power of 6. And that would be our answer. And here is another example. You can go ahead and pause the video and go for this one. Okay, so we have a base of 3 that has an exponent. So we're leaving 3, we're multiplying the exponent. So that is the 2 multiplied by the x plus 1. The 2 will multiply by the x to give us 2x. And then the 2 will multiply by the 1 to give us a positive 2. And this is over. And we have now 2 raised to the power of a negative 3. And that is going to also multiply to the x plus 1. So we have a 2 raised to the power of negative 3 times x is negative 3x. And then negative 3 times positive 1 is negative 3. So in the future video, I will also show you another way to simplify this kind of expression, or rather how to further simplify it. Okay, so this is our answer for now. In this example, we have 5 raised to the power of x minus 1 over 5 raised to the power of x plus 3. And all of that is being raised to the power of 3. You can go ahead and pause the video and go for this one. Okay, so we're just looking at the bases. The base that we have is 5, and its exponent is x minus 1. That is going to multiply with that outside. So we have 5 raised to the power of the x minus 1 needs to multiply with the 3. So both the x and the negative 1 need to multiply to the 3. So you could distribute it like this. Since this has 2 terms and that has 1 term, the 3 can multiply to the x, and that gives you a 3x. And then the 3 can multiply to the negative 1, which gives you a negative 3. And this is over, and really the exact same thing happens on the denominator. So on the denominator, you see that we have an x plus 3 and an exponent of 3 outside, and that also needs to multiply like that. So we have our base of 5, the x is going to multiply to the 3, and that gives you a 3x, and then the positive 3 multiplies to the 3, which gives you a positive 9. And then from here, do you see that we have a situation where we have the same bases that are being divided? So from exponential law 2, all we know that we need to do here is we're going to keep the base the same, and then we're going to subtract the exponents. So we're going to say the top exponent minus the bottom. That is 3x minus 3. And then we're going to say minus. Now to make sure that we actually do subtract by the 3x and the 9, you need to include brackets. So we're going to say 3x plus 9. And so this is equal to 5 raised to the power of 3x minus 3. And we can distribute that negative into those two terms. So that is negative 3x and negative 9. So by now, what you could have been doing is already changing the signs when you're subtracting, okay? So that you could just skip this step. And this would be equal to 5 to the power of, as you can see, we have positive 3x and negative 3x. They would simplify and become 0. And then negative 3 minus 9 is negative 12. And for the sake of lesson 6, I'm going to leave this answer like this. Okay. So in lesson 6, we'll speak more about negative exponents. So for now, this would be our solution to that. Hey guys, and welcome to part 5 on this series on laws of exponent. So this video is going to be another short video. And in this video, we're going to be speaking about the 5th law of exponents. Well, of course, according to my numbering, I'm just numbering it like this. And the 5th law states that anything raised to the power of 0 is always going to be equal to 1. So in this illustrative example, if we have x raised to the power of 0, it's just going to be equal to 1. So in this, all you have to focus on is what is being raised to the power of 0. Be very careful with that. So if we have 3,246,687 raised to the power of 0, well, all of these numbers, because they were just raised to the power of 0, they would just be equal to 1. Here is another example that you can go ahead and work out. So in this example, we have x to the power of 2, and that is being raised to the power of 3. but then that is being raised to the power of 0. So no matter what exponent it was raised to, as long as at the end you can see that all of this is being raised to the power of 0, then everything that was inside this bracket would really just become 1. And here's another example you can go ahead and work out. Okay, so in this example, remember when I said be careful to check what exactly is being raised to the power of 0? That's going to apply here. So we have a 3 outside the bracket. Clearly that 3 is not being raised to the power of 0. So the 3 still stays outside. And then now everything that is in here, we have negative 2 squared, but it's being raised to the power of 0. So everything inside your bracket just ends up becoming a 1. So this 3 is being multiplied by a 1. You can also write it like that if you want, multiplied by 1. And 3 times 1 just gives you 3. And that is your final answer. Here is your next example. So in this example, we have negative 2 raised to the power of 0. Be careful. Find out what is being raised to the power of 0. Remember how I said that the exponent is always very possessive and jealous? So whatever is carrying the 0 is what is going to be applied. In this case, it's not the negative 2, it's the 2 that is carrying the 0. So 2 raised to the power of 0, that's what gives us 1. So what happens with this negative? Well, it stays there. We still have the negative, and then the 2 raised to the power of 0 gives us a 1. So our answer here is actually negative 1. And here we have negative bracket 2 to the power of 0. And you can go ahead and have a go at it. So in this expression, because we have an exponent of 0, okay, we're naturally already going to start here, not because we have an exponent of 0, but because we have an exponent. And the exponent belongs to the base, always. The exponent is nothing without its base. So the 2 gets raised to the power of 0, and that gives you a positive 1, right? And you still have this negative outside the bracket. So we still have the negative, and this 2 raised to the power of 0 gives you a 1. So our answer here is negative 1. Do you see that this and the previous example that we had, the negative 2 raised to the power of 0, they're really the same expression. Okay, they're just written differently. This one really defines what this one means. It's telling you that the 2 is actually the only thing being raised to the power of 0. And then the last example for this one is negative 2 all raised to the power of 0. You can go ahead and work out this one and then play for the solution. Okay, so in this expression, let's look at the exponent of 0. What is the base that is attached to this exponent? It would be the negative 2, since we have brackets and it's been raised to 0. So everything inside here just ends up becoming 1. And so our final answer is just 1. And that is the end of this video. I hope to see you in the 6th part of this series. Hello guys, and welcome to the 6th part of the series on laws of exponents. In this video, we're going to be dealing with negative exponents. So for our illustrative example, we have x raised to the power of negative a. And we're going to simplify this expression in a way that the exponent is going to be positive. So this is how we're going to work it out. When we're looking at this expression, I want you to realize that when you have an expression, a single expression like this, naturally as a fraction, this part is already on the numerator. So if it is on the numerator, what exactly is the denominator of this fraction? Well, it has a denominator of 1 right now. So how do we get that exponent of negative a to become positive? Well, we're going to focus on the fact that it is negative. So right now we're seeing it as the problem. And so the base that is carrying the exponent, that negative exponent, is the x. The only way to make it positive is you have to move it from the numerator to the denominator. So if it was originally on the denominator, then you would have to move it to the numerator. So right now it is negative, it's on the numerator. So we're going to move it over to the denominator. And this is what happens when we do that. So I still have the fraction. This now comes to the denominator. So we have now x, and now it's raised to the power of a positive a. But what is on the numerator? Now most people say, oh, these two actually just swap places. That is not true. They do not swap places. What happens is the number on the numerator is whatever number was actually still on the numerator. I know we cannot see a number here, but there is a coefficient in front of x to the power of negative a. And that coefficient is an invisible positive 1. That's the exponent that stays on the numerator. So that positive 1 stays on the numerator. They do not swap. There's a reason I'm saying that. Okay, so this is what our expression ends up becoming, 1 over x to the power of a. Okay, so here is what we have. We have 3x to the power of negative 2. In this example, here is why I said those two numbers do not swap in the previous example. So we just have a 3x to the power of negative 2, and we need to rewrite this expression in a way that the exponent is positive. Okay, we're going to have to put it as a fraction first. Everything that is here is naturally on the numerator. So what is on the denominator? We have an invisible positive 1. Oh, we could just make it invisible now. So what happens is you're going to focus on the problem. The thing that has a problem is whatever has a negative exponent. So let's spot that negative exponent. It's the 2, the negative 2, right? What is carrying the negative 2? It's the x. That is what's carrying the negative 2. So do you see now that the 3 does not have a problem? And if the 3 does not have a problem, the 3 has no reason to move anywhere because it didn't have a problem in the first place. So what happens here is that we're going to have this x to the power of negative 2 move from the numerator to the denominator because it had a negative exponent. Now you can see this 1 as a placeholder. It's holding the place for the denominator. So as a fraction, what is going to happen is we have on the denominator, we have a 1. So let's say the 1 was still there, right? Because I don't want to just make it disappear. I want to show you what actually happens to it. So we still have that 1, that placeholder of 1. And so what goes to the denominator is this x to the power of negative 2. But that 2 will now become positive. So we now have an x to the power of positive 2. And then the 3 stays on the numerator. It didn't have a problem in the first place. Its exponent is positive. It has a natural positive exponent of 1. It doesn't move. So what actually happens here on the denominator? Well, you still have the 3 on the numerator, and on the denominator, it's really like 1 multiplied by x squared, which still gives you x squared. That's why you usually have a situation where you have this, and it becomes that. So another way of looking at how this would simplify is like this. You're looking at the fact that you have a negative 2, and the base that is carrying the negative 2 is the x. So naturally, everything that is here is on the numerator. Meaning the 3 is on the numerator. It doesn't have a problem, so it stays 3. Then on the denominator, this will now move to the denominator from the numerator. And we have x to the power of positive 2. That's actually how that moves. Whatever does not have a negative exponent does not need to move from wherever it is. It will just stay there. Okay, so look at our next example. We have y to the power of negative 3 divided by 2, x to the power of negative 2. You can go ahead and have a go at this one. Okay, so to simplify this expression, what we're going to do is, it's already a fraction, so we don't have to put it over 1. We can just leave it as a fraction. So we're going to look for the things that have negative exponents, and that's a negative exponent. What is carrying the negative exponent? The y. So that needs to move. It is currently on the numerator. It needs to move to the denominator. What else has a negative exponent? That's a negative exponent. So the x to the power of negative 2, that needs to move as well. So what happens is we just have on the numerator, what is coming to the numerator is this x to the power of negative 2. But it's now an x to the power of positive 2. And then we have over. Now, do you see that on the denominator, we already had a 2. And this 2 does not have a negative exponent. In fact, its exponent is a positive invisible 1. So we're going to leave it where it is because it didn't have a problem. It was on the denominator, you leave it on the denominator. And then what else is going to be here? Well, this had a negative exponent. It was on the numerator, so we will move it to the denominator. So this is y to the power of positive 3. And this would be our answer. Okay, so let's work more with numbers now. We have 2 to the power of negative 1. So without a calculator, simplify this expression. Okay, so in this case, the 2 has a negative exponent, so it needs to move. Where is it currently? It is on the numerator, okay? Because you can write this as a fraction as 2 to the power of negative 1 over 1. So what happens is that 2 to the power of negative 1 will come to the denominator. You don't have to rewrite that 1 there. It's really a placeholder. It's holding the place of the denominator. So this comes to the denominator and becomes a 2 to the power of positive 1. And then what's on the numerator? Well, whatever was on the numerator besides this number. There is actually an invisible 1 here. In other words, you can also see that 1 on the numerator as a placeholder that is there. That's what was on the numerator. It's not a swap, and so I'm going to even write it in different colors. There was an invisible 1 on the numerator. So what happens here is we just have 1 over 2 raised to the power of 1, which just stays 2. So our answer is a half. And here's your next example. You can go ahead and work this out. So in this example, again, you always spot whatever has a negative exponent. What has a negative exponent is the 5. So that needs to move. This is already a fraction. I don't have to write it as a fraction again. So what's going to happen is this 5 to the power of negative 2 needs to move to the numerator so that its exponent is positive. When it moves to the numerator, this 1 is like a placeholder. It becomes 5 to the power of positive 2. Okay, the placeholder, you can say 1 multiplied by that, but it's really not necessary. It's just holding the place of the numerator. And so 5 squared just gives you 25. And that would be our answer. Likewise, if we had 7 to the power of negative 2, what happens is the 7 has an exponent that is negative. It's currently on the numerator. It needs to come down to the denominator so that its exponent is positive. So when it comes down to the denominator, it becomes 7 to the power of positive 2. And what's on the numerator? There is a placeholder of 1. It's like the coefficient of the 7 to the power of negative 2 is an invisible 1 that is there. So that's what stays on the numerator. And so we have 1 over 7 squared is 49, and that's our answer, 1 over 49. Okay, so here is another example. You can go ahead and go for this one. So in this example, as you can see, nothing has the same basis on the numerator and on the denominator. So nothing's really going to simplify with each other. All we have to do here is find everything that has a negative exponent so that we can move it to its respective place. First of all, I see that b has a negative exponent of 2. So I've already decided that b needs to move to the denominator. I can start off by writing this as a. A does not have a negative exponent. In fact, it has a positive exponent of 1, so it stays a. The b, however, needs to move to the denominator. So that's going to become b to the power of positive 2. If I keep on moving, I see d, and so I'm going to say d, and that doesn't move anywhere. It doesn't have a negative exponent, so it stays there. Then we have an e to the power of negative 3. That has a negative exponent. It needs to move to the denominator. So that is now e to the power of positive 3. Then now we can look at the denominator. On the denominator, we have c to the power of negative 3. Since its exponent is negative, it needs to move to the numerator. And so that is going to be c to the power of a positive 3. And then we see f also has a negative exponent. It's on the denominator. It needs to move to the numerator, so it's going to be f to the power of positive 1, which we don't have to write. And then what you can do to just brush this up is you can write it in alphabetical order. So the A is first, and then on the numerator, what's going to come after the A should be the C. But the C is raised to the power of 3. And then we have a D raised to the power of invisible 1, and we have F. And this is over, and this is in alphabetical order. B squared is coming before E cubed. And that would just be our solution. So it's really about finding what has the negative exponent and moving that. Things don't just switch places. They're not switching places from the numerator to the denominator. Okay, so here we have this expression. In this one, I will show you a shorter method as well. So I will show you the step-by-step method and then the shorter method. So like the law 2, exponential law 2, all we're doing here is dividing. So if the bases are the same and we're dividing, we need to subtract the exponents. But notice that we have coefficients. So we need to say 12 divided by 3 first. 12 can divide by 3, and 12 divided by 3 just gives us 4. Remember, this answer is naturally on the numerator. Then we have an x squared, and this is being divided by x. So the bases are the same. We're dividing, subtract exponents. So we have x to the power of 2 minus 1, which is 1, and we don't have to write that 1. Then over here, we have a y. And we have y to the power, the invisible exponent of 1, divided by y to the power of 3. What happens there? Well, if you say y to the power of 1, right, that is there, minus 3, you're going to get 1 minus 3 gives you negative 2. Okay. Then when you have this, you can simplify this further. See it as all of these are on the numerator naturally. If you want to rewrite this so that the exponents are positive, you see that the only thing with a problem here is this. That has a negative exponent. So the y needs to move from where it currently is. It's on the numerator. It needs to move to the denominator. So we're going to have 4x, which does not have a problem. You don't move that one, over y squared. Okay, so that would be how to simplify that in a step-by-step method, in the basics method really. But now I'm going to also show you a quicker method of simplifying this. So here's another method that you can do, and I call this the cancel method. You can just cancel out things that are common. So I'm going to look at this expression, and I'm going to look at the numerator and denominator and ask myself what is common. I'm going to keep dividing by what is common. Now, with the numbers is quite simple because you know that 12 divided by 3 is 4. You could have also seen it as between 12 and 3, the highest common factor is 3. So I could have said 12 divided by 3 is 4 and 3 divided by 3 is 1, right? Well, I'm also going to do that with the variables. I'm looking at x squared and I'm saying what is common between x squared? What is the highest common factor between x squared and x? If you expand x squared, it's really just x multiplied by x. And x is just x. So if you look at that, what would simplify? What is your highest common factor? What is common here that is also here? It would just be an x. So what happens is an x cancels out in both expressions and you're only left with an x. So this is how we cancel that out. We look at the fact that you have x squared and you have x, and the highest common factor is x. So we're going to say x squared divided by x. That would just be an x. So you can rewrite a 1 there so that you know it's x to the power of 1 that is remaining. And x divided by x, that simplifies to 1. So that really just cancels out. And then we can do the same thing to the y. So with the y, you see that we have a y on top, which is just y, and a y to the power of 3, which is made up of y multiplied by y multiplied by y. What is the highest common factor between these? So what is the highest thing that is common? We have one y here and one y here. That would be what is common between those two expressions. So we're going to divide or cancel out a y. On the numerator, when we do this, this is what happens. So on the numerator, if you cancel out a y, you're not left with any y because there's just one y on the numerator. But on the denominator, if you cancel out a y, only one of it is cancelling because you're cancelling out a y. And so out of that y to the power of 3, what you're left with is a y to the power of 2. Just like we can see here, if those two cancels, you're left with y squared. And then to simplify this further, you can just go ahead and say what is left on the numerator. So in this method, you have to work through it very neatly so that you do not confuse yourself with the numbers that you're writing. So we have 4 still on the numerator, and then we have an x to the power of positive 1, which I don't have to write. And then the y is gone. Over, and I have a 1. Now I can choose to write this 1, but the only time I actually need to write the 1 is if nothing is left on the denominator. But you see that we have a y squared, so I don't really have to write that 1 because it will still multiply by the y squared and stay a y squared. So I just have y squared. So do you see how we still end up with the same answer, but this method seems much shorter? Okay, so really they're both important. This would be the basic way of working it out. This is how you'd be taught how to do this in maybe grade 8, and then you would advance to this method in grade 9 and really just use this method. Okay, so let's try another example. So here is another example. You can go ahead and work on this one. Okay, so in this method, in this question, I'm going to be using the second method. The reason why is because the second method is really an advanced method from the first. The first one is more of a basic. And the second one, it really helps you to just simplify these expressions faster. So what I'm going to do is, I'm looking at the 9 and I'm dividing it by -3. And I know that whatever answer I get is going to be on the numerator. 9 divided by -3 is just -3. And then we have the x to the power of 2 divided by x to the power of 3. I'm going to look at those two and see what is common between the both of them. It is going to be x to the power of, what is the highest common factor? X to the power of 2, because we have an x to the power of 2 here, and an x to the power of 2 is also inside this x to the power of 3. So that's what's going to cancel. The x to the power of 2 cancels here, and you'll be left with nothing here because there was only an x to the power of 2. And here x to the power of 2 cancels, but because there was an x to the power of 3, you would have an x to the power of 1 remaining there. Then with the y's, what happens? Well, you have a y squared and a y to the power of 4. What is your highest common factor? It would be y to the power of 2, because y to the power of 2 can go in here, and y to the power of 2 can also go in here because there's y to the power of 4. There's even more y's in here. So what cancels is y to the power of 2. That cancels and there's nothing left on top since there was only a y squared. And here when y squared cancels, what are you left with? How many y's multiplied are you left with? You're left with y to the power of 2 left. And then we're going to do the same thing to the z. We have z to the power of 6 and z to the power of 3. What's your highest common factor between z to the power of 6 and z to the power of 3? That would be z to the power of 3, because z to the power of 3 can go into this and into this. When we cancel z to the power of 3 here, you're left with z to the power of 3 remaining. And when you cancel that here, you're left with nothing really, or just 1. Because if I expand that, z to the power of 6 is made up of 6 sets of z's being multiplied. And z to the power of 3 is made up of 3 sets of z being multiplied. And so when you're looking at what's common, you're seeing what can cancel in both. Well, there's 1, there's 2, there's 3. That's why z to the power of 3 is common. And that's why z to the power of 3 was left on that, because from the z to the power of 6, you see that you still have 3 sets of z multiplied left. And here, what's left? Nothing. Okay, so this is a quicker way of simplifying this. And now that we have cancelled, but you just have to be very careful and neat with this so that you don't mix up numbers. Now we're just going to look at what is left. So with the variables, what's left? That's done, that's gone, that's gone. The only thing left on the numerator is this, z to the power of 3 over, in the variables, what do we have left? Well, we have an x to the power of 1, which you can just write as x. And if we keep moving, we have a y squared still remaining, y to the power of 2. and then there's nothing left. So you can use this method if you want to, but you need to be careful and neat with it so that you do not mix up numbers. So that is our answer. Okay, so that is the end of this video. I hope you enjoyed it. If you enjoyed it, please make sure to leave a like and subscribe for more content like this. Stay safe, and I hope to see you guys in the future videos.